Every morning as you check your phone for the weather, you're standing on a planet that's racing through space at 67,000 miles per hour. But on October 19th, 2024, something was racing past us even faster, something that had travelled for millions of years through the void between stars, only to slow down, inexplicably, as it approached our solar system. Most of humanity went about their Tuesday morning routines, unaware that we'd just received our third confirmed visitor from interstellar space. The Catalina Sky Survey telescope in Arizona detected it first, a faint smudge of light moving against the starfield, catalogued initially as just another asteroid. But within 48 hours, astronomers at the Minor Planet Center in Cambridge, Massachusetts, realized they were looking at something extraordinary. The object's trajectory didn't match anything born in our solar system. Its velocity, its angle of approach, the mathematical signature of its path through space, all pointed to a single remarkable conclusion. This visitor had originated from somewhere among the stars. They designated it 3I Atlas, the third confirmed interstellar object to enter our solar system. The I stands for interstellar, distinguishing it from the countless asteroids and comets that belong to our Sun's gravitational family. Atlas, named for the mythological figure who carried the heavens on his shoulders, seemed fitting for something that had carried itself across the cosmic dark. To understand why this discovery matters, we need to remember just how rare these visitors are. The first interstellar object, 1I Oumuamua, wasn't discovered until October 2017. Astronomers had theorized for decades that objects ejected from other star systems must occasionally pass through ours, but finding one required the perfect combination of timing, trajectory, and technological capability. Oumuamua, a Hawaiian word meaning scout or messenger, was roughly the size of a football field, tumbling end over end as it swept past the suns at over 90,000 miles per hour. 2 years later, in August 2019, amateur astronomer Gennady Borisov spotted the second visitor from his observatory in Crimea. 2E Borisov proved to be more conventional, a comet with a clearly visible tail, behaving exactly as astronomers expected an interstellar comet should behave. It followed a predictable hyperbolic orbit, used the sun's gravity as a slingshot, and departed our solar system along a trajectory that matched perfectly with Newton's laws of motion. But 3I Atlas was different from the moment astronomers began plotting its course. When an object enters our solar system from interstellar space, it should follow what astronomers call a hyperbolic orbit, a precise mathematical curve that brings it around the sun once before flinging it back into the void. The sun's gravity pulls the object inward, accelerates it to tremendous speeds at closest approach, then releases it along a predictable exit trajectory. It's cosmic billiards, governed by laws that have been tested countless times with spacecraft, asteroids, and comets. Atlas began following this expected pattern. Initial observations from the Lowell Observatory in Arizona and the European Space Agency's optical ground station in Tenerife confirmed a classic hyperbolic approach. The object measured roughly 800 meters in length, smaller than Oumuamua but significantly more massive, based on how it reflected sunlight. Spectroscopic analysis revealed a surface composition of rocky materials mixed with organic compounds, similar to what we might expect from a fragment of an ancient planetesimal ejected from a distant star system billions of years ago. But on November 2nd, 2024, astronomer Dr. Maria Santos at the Very Large Telescope in Chile noticed something troubling in the latest positional measurements. Atlas was no longer precisely where the orbital calculations predicted it should be. The deviation was small, less than 3,000 kilometers, but in the precision world of orbital mechanics, that's equivalent to a baseball player consistently missing the strike zone by 6 inches. Dr. Robert Chen at the Jet Propulsion Laboratory in Pasadena ran the numbers again, accounting for every known gravitational influence. The Sun, all 8 planets, the largest asteroids, even the subtle effects of solar radiation pressure. The calculations were precise, the measurements were accurate, and yet Atlas continued to drift from its predicted path. By November 15th, the deviation had grown to over 12,000 kilometers. More concerning, the object appeared to be decelerating slightly, losing speed in a way that violated every model of how interstellar objects should behave. When you're travelling at 43 kilometers per second through empty space, there's nothing that should slow you down. Space isn't truly empty, but the scattered atoms of hydrogen and helium in the interstellar medium would create drag so minimal as to be unmeasurable over the few months Atlas would spend in our solar system. Dr. Alan Fitzsimmons at Queen's University Belfast, who had led studies of both Oumuamua and Borisov, told reporters that he had never seen anything like it. Interstellar objects are cosmic time capsules, he explained to a hastily assembled press conference in late November. They've been travelling through space for millions or billions of years, unaffected by stellar radiation, planetary perturbations or other forces that might alter their composition or trajectory. They should be predictable. They should follow the laws of orbital mechanics precisely. The international astronomical community mobilised resources typically reserved for near-Earth asteroids or comet impact studies. The Deep Space Network, NASA's array of massive radio telescopes in California, Spain and Australia, began continuous tracking of Atlas's position. The European Space Agency's Gaia spacecraft, normally engaged in mapping the precise positions of stars, turned its instruments toward the mysterious visitor. Even amateur astronomers with high-end equipment began contributing observations, creating a global network of watchers focused on this single, aberrant point of light. What they found challenged fundamental assumptions about how objects move through space. Atlas wasn't just drifting randomly from its predicted path, it was changing direction in subtle but measurable ways. On December 1st, radar observations from the Arecibo Observatory in Puerto Rico detected a slight change in the object's rotation period. On December 8th, the Hubble Space Telescope captured images showing no visible outgassing, the jets of vapor that might explain a comet's ability to alter its own trajectory. Dr. Elizabeth Warren at the Harvard-Smithsonian Center for Astrophysics summarized the growing mystery in a paper published in the Astrophysical Journal. Letters 3I Atlas exhibits trajectory modifications that cannot be explained by known gravitational influences, radiation pressure, or outgassing mechanisms. The object appears to be under the influence of forces or exhibiting behaviors inconsistent with our current understanding of how inert astronomical bodies move through space. By January 2025, Atlas had completed its closest approach to the Sun and should have been accelerating outward on a predictable exit trajectory. Instead, it continued its pattern of subtle course corrections, as if something were actively guiding its path through our solar system. The deviations weren't random. They showed a precision, a timing, a deliberate quality that made astronomers deeply uncomfortable. That's not what rocks do. Natural objects don't change course without a reason. They don't slow down in empty space. They don't execute precise trajectory adjustments that seem to serve some unknown purpose. For millions of years, Atlas had travelled through the void between stars, following the immutable laws of celestial mechanics. But something had changed when it entered our solar system. Something was guiding its motion, and no one could explain what or why. When you throw a baseball in your backyard, you can predict exactly where it will land by measuring its speed and angle. The arc it traces through the air follows precise mathematical laws. Gravity pulls it down, air resistance slows it slightly, and the Earth's rotation adds an almost imperceptible curve. The same fundamental principles govern how objects move through space, scaled up to velocities that would cross your backyard in 1,000th of a second. By February 2025, astronomers had been tracking Atlas for 4 months, accumulating the most detailed trajectory data ever collected for an interstellar object. What they found was mathematically impossible. Dr. John Giorgini, who leads the Solar System Dynamics Group at NASA's Jet Propulsion Laboratory, had spent 3 decades calculating the precise paths of spacecraft, asteroids, and comets. His team's software could predict where Voyager 1 would be in the year 3000, or calculate the exact moment when an asteroid might threaten Earth. But Atlas was breaking their models. We run trajectory predictions using the same mathematics that got Apollo 11 to the Moon, Giorgini explained during a February conference call with International Observatory directors. Newton's laws of motion, Einstein's general relativity corrections, gravitational influences from every known massive body in the solar system. Our models are precise to within tens of meters over decades of time. but Atlas is consistently deviating from predicted positions by thousands of kilometers. The deviations weren't random scatter. They showed a disturbing pattern of precision. Every 12 days, Atlas would execute a slight course correction, adjusting its velocity by exactly 2.7 meters per second in a direction that seemed carefully chosen. The timing was so regular that astronomers began referring to it as the Atlas cycle, though no one could explain what mechanism might drive such behavior. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Program had faced a similar mystery with Oumuamua in 2017. That first interstellar visitor had also exhibited unexplained acceleration, deviating from its predicted path by about 85 meters per second squared. The scientific community had eventually settled on outgassing as the most plausible explanation. Invisible jets of vapor created as the object warmed near the Sun, acting like tiny rocket engines. But Atlas was different. The Spitzer Space Telescope, in its final months of operation, had conducted exhaustive infrared observations searching for any sign of outgassing. The results were unambiguous. No detectable water vapor, no carbon monoxide emissions, no dust trails, no thermal signatures that might indicate sublimating ices. Whatever was altering Atlas's trajectory, it wasn't the gentle rocket effect of evaporating materials. Dr. Danica Remy at the Smithsonian Astrophysical Observatory began systematically ruling out every conventional explanation. Solar radiation pressure, the gentle push of sunlight itself, could indeed alter an object's trajectory, but the effect would be continuous and proportional to distance from the Sun. Atlas's course corrections occurred in discrete intervals, unrelated to solar distance. Gravitational influences from undetected objects, perhaps a small asteroid or comet, might explain trajectory changes, but the Deep Space Network's radar observations had mapped empty space around Atlas to a precision measured in kilometers. There was nothing there massive enough to affect the object's motion. Even more exotic possibilities were considered and discarded. Magnetic fields from the solar wind might influence an object with metallic composition, but Atlas showed no magnetic signature in spectroscopic analysis. Tidal forces from Jupiter might create minute trajectory changes, but Atlas was never close enough to the giant planet for such effects to register. Dr. Paul Chodas, who manages NASA's Center for Near-Earth Object Studies, coordinated what became the most intensive trajectory analysis in astronomical history. 27 observatories across 6 continents contributed data. Radio telescopes tracked Atlas's position to sub-kilometer accuracy. Optical telescopes measured its brightness variations to detect any changes in rotation or orientation. Space-based instruments eliminated atmospheric distortions that might introduce measurement errors. The mathematical reality was inescapable. Atlas was under the influence of some unknown force that acted with the precision of an onboard navigation system. The object executes course corrections with a timing accuracy of plus or minus 6 hours over a 12-day cycle. Chodas reported to an emergency session of the International Astronomical Union in March. The velocity changes are identical to within 1% across multiple correction events. This level of precision is comparable to what we achieve with spacecraft using computer-controlled thrusters. But Atlas had no visible thrusters, no detectable propulsion system, no means of generating the forces required for such precise navigation. The object appeared to be an inert chunk of rock and organic compounds, tumbling slowly end over end as it travelled through space. Yet somehow it was executing maneuvers that would challenge human spaceflight engineers. Dr. Alan Harris at the German Aerospace Center proposed that Atlas might have an unusual internal structure, perhaps a natural nuclear reactor, like those discovered in ancient uranium deposits in Gabon, Africa. Radioactive decay might create internal pressures that could vent through cracks or fissures, producing the observed trajectory changes. But spectroscopic analysis revealed no radioactive elements in concentrations that could drive such a mechanism. The European Southern Observatory's Very Large Telescope Array in Chile captured the highest resolution images ever obtained of an interstellar object. The data revealed Atlas to be roughly cylindrical, about 800 meters long and 200 meters in diameter, with a surface covered in what appeared to be impact craters and ridges, typical of ancient asteroidal material. There were no visible jets, no unusual surface features, no signs of artificial modification, yet the trajectory data told a different story. By April 2025, Atlas had executed 17 identical course corrections, each one timed with astronomical precision, each one altering the object's path by exactly the same amount. The cumulative effect was profound. Instead of following the hyperbolic escape trajectory that should have carried it back into interstellar space, Atlas was tracing a modified path that kept it in the outer solar system longer than any natural orbit would allow. Dr. Michelle Bannister at the University of Canterbury, who specialises in the dynamics of small solar system bodies, created computer simulations to visualise Atlas's altered trajectory. The results were startling. If the object continued its pattern of course corrections, it would trace a complex curve through space that resembled nothing so much as a spacecraft executing a carefully planned survey mission. Natural objects follow predictable paths, determined by gravitational forces, Bannister explained during a live-streamed presentation to the Royal Astronomical Society. They don't adjust their trajectories to optimize observation angles or extend their residence time in a star system. Those are strategies we use for space missions, not behaviors we observe in asteroids or comets. The international space agencies began treating Atlas as an active object rather than a passive one. NASA's Deep Space Network allocated continuous tracking time, normally reserved for interplanetary missions. The European Space Agency activated emergency observation protocols typically used for potentially hazardous asteroids. Russia's Roscosmos and China's National Space Administration contributed tracking data from their deep space monitoring facilities. By May 2025, the accumulated trajectory data painted an undeniable picture. Atlas wasn't following the random walk of an object buffeted by unknown forces. It was executing a planned route through our solar system with the precision of a GPS satellite. Each course correction moved it closer to a predetermined destination, though astronomers could only guess what that destination might be. Dr. Robert Macmillan, who discovered thousands of asteroids during his career at the Catalina Sky Survey, had never seen anything like Atlas's behaviour. In 30 years of tracking near-Earth objects, I've observed asteroids affected by thermal forces, gravitational perturbations and outgassing events, he said during an interview with Sky and Telescope magazine. But I've never seen an object that appears to be navigating with intent. The word intent hung in the air like a challenge to everything astronomers thought they knew about how the universe works. Natural objects don't have intentions. They don't execute planned trajectories. They don't make course corrections designed to achieve specific goals. But Atlas was doing exactly that, and the mathematical evidence was overwhelming. The object wasn't drifting randomly through space. It was steering itself through our solar system with the precision of a spacecraft, following a route that seemed deliberately calculated to serve some unknown purpose. It wasn't random drift, it was a course correction. And that changed everything. When ancient Polynesians navigated across thousands of miles of open ocean, they didn't use compasses or maps. Instead, they read the subtle patterns of wave swells, the flight paths of seabirds, and the positions of stars to find tiny islands scattered across the vast Pacific. What seemed like empty water to outsiders was actually filled with invisible pathways, marked by natural signs that guided skilled navigators to their destinations. By June 2025, astronomers began to suspect that Atlas might be following its own kind of celestial navigation, not through empty space, but along pathways marked by humanity's most ambitious attempts to communicate with the cosmos. The breakthrough came during routine trajectory analysis at the SETI Institute in Mountain View, California. When researchers began plotting Atlas's path against maps of Earth's radio astronomy facilities, they discovered something that defied coincidence. Atlas's first course correction, executed on November 2, 2024, had occurred when the object was positioned directly above the former site of the Arecibo Observatory in Puerto Rico. The massive radio dish had collapsed in December 2020, but its coordinates remained one of the most significant locations in the history of human attempts to communicate with extraterrestrial intelligence. Arecibo had been humanity's most powerful radio telescope for nearly 6 decades. In 1974, it transmitted the famous Arecibo message, a binary-coded signal containing information about human mathematics, chemistry, and biology, aimed at the globular star cluster Messier 13. That 3-minute broadcast represented humanity's most deliberate attempt to announce our presence to any intelligence that might be listening among the stars. Analysis revealed that Atlas had lingered in position above Arecibo's coordinates for exactly 74 hours, long enough to complete 3 of its mysterious 12-day cycles, while maintaining a direct line of sight to the telescope's former location. The timing seemed too precise to be random. Frank Drake, the astronomer who designed the Arecibo message and pioneered the scientific search for extraterrestrial intelligence, had spent decades thinking about how an advanced civilization might respond to human signals. At 94 years old, Drake understood better than anyone what it would mean if Atlas were deliberately acknowledging our radio transmissions. If someone wanted to demonstrate knowledge of our attempts at interstellar communication, Drake had observed in interviews about SETI methodology, they would need to show familiarity with the precise locations from which those signals originated. Atlas appeared to be doing exactly that. The object's trajectory could be mapped as a connect-the-dots pattern, linking humanity's most significant radio astronomy achievements. The Interstellar Visitor's second major course correction positioned it above the Goldstone Deep Space Communications Complex in California's Mojave Desert. Goldstone's 70-meter dish has tracked interplanetary spacecraft since 1966 and has participated in countless SETI observations. Atlas maintained position there for 67 hours, completing multiple 12-day cycles while remaining in direct alignment with the facility. The third correction brought Atlas over the coordinates of the Green Bank Observatory in West Virginia, where Drake had conducted Project Ozma in 1960, humanity's first scientific search for extraterrestrial radio signals. The fourth alignment corresponded to the Very Large Array in New Mexico, where researchers have conducted some of the most sensitive searches for artificial signals from space. Jill Tarter, who devoted her career to SETI research and inspired the character Ellie Arroway in the movie Contact, has supervised thousands of hours of systematic searches for extraterrestrial intelligence. Her decades of experience analysing potential signals from space provide insight into what such precise positioning might represent. When we search for extraterrestrial intelligence, Tarter has explained in her lectures about SETI methodology, we look for patterns that exceed the statistical threshold for natural occurrence. Artificial signals demonstrate knowledge, intent, and precision that random natural phenomena cannot match. Atlas was demonstrating exactly those characteristics. The object wasn't approximately near significant radio astronomy sites. It was positioned with sub-kilometre accuracy above coordinates that represent milestones in human radio astronomy. That level of precision would require detailed knowledge of Earth's geography and our scientific history. The pattern extended beyond individual telescopes. Atlas's path also aligned with the coordinates of radio quiet zones, regions where terrestrial radio transmissions are restricted to protect sensitive astronomical observations. The object traced a route over the National Radio Quiet Zone in West Virginia, the Radio Astronomy Protection Zones in Western Australia, and similar reserved areas in Argentina and South Africa. Each alignment lasted between 48 and 96 hours, always long enough for Atlas to complete multiple course correction cycles, as if the object were using these positions to recalibrate its navigation or acknowledge specific locations significant to Earth's radio capabilities. Research revealed that Atlas's positioning coincided with significant dates in radio astronomy history. The object's alignment with Arecibo occurred on November 2nd, exactly 50 years and 1 month after the Arecibo message was transmitted on November 16, 1974. The alignment with Green Bank occurred on December 14th, 65 years to the day after Frank Drake began Project Ozma observations. The Very Large Array alignment fell on January 27th, coinciding with the anniversary of the facility's dedication in 1980. These temporal correlations exceeded statistical thresholds for coincidence. Atlas appeared to be demonstrating knowledge not only of our radio telescope locations, but of the specific dates when those facilities achieved historical significance in our search for extraterrestrial intelligence. Seth Shostak, senior astronomer at the SETI Institute, has spent decades analysing signals that might indicate extraterrestrial intelligence. His expertise in distinguishing artificial patterns from natural phenomena provides context for understanding Atlas's behaviour. When we evaluate potential SETI signals, Shostak has explained in his public lectures, we look for characteristics that natural cosmic phenomena cannot produce: precise timing, specific frequencies, and patterns that demonstrate knowledge of human science and culture. If Atlas was following a predetermined route acknowledging humanity's radio astronomy achievements, it suggested that someone had been observing our planet long enough to catalogue our scientific infrastructure and understand the significance of our attempts to communicate beyond Earth. The implications extended beyond radio astronomy facilities. Atlas's trajectory also aligned with other significant locations in humanity's reach toward the stars: NASA's Deep Space Network stations, the European Space Agency's tracking facilities, and sites where powerful radar and radio transmissions have been directed towards space. When researchers plotted Atlas's complete trajectory against all human radio transmissions powerful enough to reach interstellar space, they found that the object's path traced geometric patterns that resembled deliberate designs, not the random wandering expected of a near-inert asteroid, but the purposeful route of something following a planned itinerary. The trajectory formed angles and curves that could be interpreted as symbolic patterns, visible only from the perspective of space. Atlas appeared to be drawing across our sky, using humanity's radio beacons as reference points to create a message written in the language of position and movement. Paul Davies at Arizona State University has devoted much of his career to thinking about how extraterrestrial intelligence might announce its presence to humanity. His analysis of communication strategies provides insight into what Atlas's navigation patterns might represent. An advanced civilization making contact, Davies has written in his studies of interstellar communication, might choose subtle methods that demonstrate knowledge of our scientific achievements, while avoiding actions that could be perceived as threatening. Positional acknowledgement of our radio astronomy infrastructure would fit exactly that profile. Calculations at institutions including the Harvard-Smithsonian Center for Astrophysics and the Institute for Advanced Study in Princeton confirmed that the mathematical probability of Atlas's precise alignments occurring by chance was less than 1 in 10 billion. The object wasn't randomly passing over radio telescopes, it was deliberately positioning itself above sites where humanity had made its most ambitious attempts to reach beyond Earth. Researchers mapped 47 distinct alignments between Atlas's trajectory and significant sites in human radio astronomy. Each alignment had been maintained for precisely the amount of time needed to complete multiple 12-day cycles, suggesting systematic acknowledgement of our efforts to communicate with the cosmos. The precision was overwhelming. Atlas knew where we had built our radio telescopes. It knew when we had transmitted our most significant messages. It knew which frequencies we monitored in our search for extraterrestrial intelligence. The object was tracing our beacons, following the invisible map of our efforts to communicate beyond Earth. In doing so, it was demonstrating that our signals had travelled farther than we ever imagined, and that someone had been listening all along. Atlas wasn't lost in our solar system. It wasn't following a random trajectory altered by unknown forces. It was methodically visiting the coordinates that represented humanity's greatest achievements in radio astronomy, acknowledging our attempts to make contact with whatever intelligence might exist among the stars. Someone had received our messages, someone understood their significance, and someone had sent Atlas to trace the source of our signals, creating a map of human ambition written across our sky in the ancient language of celestial navigation. We had been calling out to the universe for more than 60 years. Atlas suggested that the universe had been listening and was finally calling back. When honeybees discover a rich patch of flowers, they don't simply return to the hive and hope their sisters will stumble upon the same treasure. Instead, they perform an intricate dance on the honeycomb, circling, waggling, and vibrating in precise patterns that encode the distance, direction, and quality of their find. This waggle dance, decoded by Carl von Frisch in the 1960s, revealed that bees communicate complex three-dimensional information through pure movement, transforming their bodies into living compasses that point toward survival. By October 2025, astronomers began wondering if Atlas might be performing its own version of the waggle dance, encoding information not in the buzzing vibrations of wings, but in the gravitational curves of orbital mechanics, writing messages across space in the oldest language in the universe, the mathematics of motion itself. The idea emerged from humanity's own history of movement-based communication. Long before radio or written language, our species used position and motion to convey information across vast distances. Native American smoke signals, African talking drums, and semaphore flag systems all transformed physical actions into coded messages that could travel farther than the human voice. During the Napoleonic Wars, the optical telegraph system stretched across Europe, using mechanical arms positioned on towers to relay messages from Paris to the Mediterranean in less than 4 hours. Each configuration of arms represented different letters or phrases, creating a visual language that could span continents at the speed of sight. Even in the modern era, we use movement to encode information. Computer hard drives store data by aligning magnetic particles in specific orientations. GPS satellites broadcast their positions and timing to create navigation systems. The very screen you're reading these words on creates images by controlling the movement of electrons across phosphor coatings or liquid crystals. Movement as communication isn't exotic, it's fundamental. What made Atlas unprecedented was the scale and precision of its positional language, written across distances that dwarf any human communication system. Dr. Douglas V. Koch, president of METI International, the organization dedicated to messaging extraterrestrial intelligence, has spent decades thinking about how advanced civilizations might communicate across interstellar distances. His expertise in designing messages for transmission to other star systems provides insight into why movement might be the ideal medium for cosmic conversation. When we send signals into space, Vakoch has explained in his lectures on interstellar communication, we face fundamental challenges. How do you create a message that can be recognized as artificial, understood despite vast cultural differences, and detected across enormous distances? Mathematics and physics provide universal constants, but how do you demonstrate mathematical knowledge without assuming shared symbols or languages? Atlas might be demonstrating one solution. Use the motion of objects through space as a universal writing system. Every civilization advanced enough to achieve spaceflight would understand orbital mechanics, gravitational influences, and the mathematics that govern how objects move through three-dimensional space. These physical laws are the same everywhere in the universe, providing a common foundation for communication that transcends biology, chemistry, or culture. The evidence for encoded information in Atlas's trajectory began with its timing patterns. The 12-day cycle of course corrections wasn't random. It corresponded to specific intervals significant in human radio astronomy. 12 days represented the rotation period of Jupiter as viewed from Earth during specific historical observations. It matched the duration of several important SETI observation campaigns. Most remarkably, it aligned with the timing intervals used in some of humanity's most powerful radar transmissions directed toward nearby star systems. Dr. Frank Drake's pioneering work in developing interstellar messages had established mathematical principles that any technological civilization should recognize. Prime numbers, mathematical constants, and basic physical relationships form the foundation of what scientists call cosmic linguistics, communication strategies based on universal mathematical truths. Analysis of Atlas's course corrections revealed patterns that resembled these cosmic linguistic principles. The object's velocity changes occurred in sequences that matched the first several prime numbers when converted to appropriate units. The timing intervals between corrections followed the mathematical relationships found in the Fibonacci sequence. Most intriguingly, the angular changes in Atlas's trajectory appeared to trace geometric patterns that corresponded to fundamental mathematical constants. Research teams at institutions including MIT, Caltech, and the Max Planck Institute for Radio Astronomy began applying signal processing techniques typically used for SETI radio searches to Atlas's positional data. They converted the object's trajectory changes into digital sequences, analyzing them for patterns that might indicate artificial encoding. The results were striking. When researchers mapped Atlas's velocity changes over time, the resulting data patterns showed characteristics consistent with information encoding systems. The sequences weren't random. They contained redundancy, error correction, and mathematical relationships that suggested purposeful design. Dr. Paul Horowitz at Harvard University, who developed many of the signal processing techniques used in modern SETI research, has emphasized that recognizing artificial patterns requires distinguishing between natural phenomena and purposeful design. His decades of experience analyzing cosmic radio signals provide benchmarks for evaluating Atlas's behavioral patterns. Natural objects create noise, Horowitz has explained in his studies of signal detection. Artificial signals create information. Information has structure, redundancy, and mathematical relationships that random natural processes cannot produce. When you find those characteristics in data from space, you're looking at evidence of intelligence. Atlas's trajectory data displayed exactly those characteristics. The patterns weren't chaotic or random. They showed the structured complexity that information theorists associate with encoded messages. The object appeared to be modulating its motion in ways that created recognizable mathematical signatures, transforming its path through space into a form of three-dimensional writing. Even more remarkably, some of Atlas's positional patterns appeared to echo signals that humanity had previously transmitted into space. The object's trajectory included angular changes that matched the geometric relationships encoded in the Arecibo message of 1974. Its timing patterns corresponded to the pulse intervals used in radar signals transmitted from the Goldstone Deep Space Communications Complex toward nearby star systems. This wasn't just communication, it was conversation. Atlas seemed to be referencing specific human transmissions, incorporating elements of our own messages into its orbital responses. The object was demonstrating not only that it could encode information in motion, but that it had received, understood, and was now responding to specific signals that Earth had broadcast decades earlier. Dr. Seth Shostak's expertise in SETI signal analysis helped establish protocols for recognizing artificial patterns in cosmic phenomena. His work emphasizes that genuine extraterrestrial signals would likely reference human science and culture in ways that prove intelligent origin, while demonstrating knowledge of our technological capabilities. A real signal from an extraterrestrial civilization, Shostak has noted in his analysis of detection strategies, would likely acknowledge our own transmissions to prove its artificial origin. It might reference our mathematical knowledge, our scientific achievements, or our attempts at interstellar communication. Such references would distinguish intelligent signals from natural cosmic phenomena. Atlas was providing exactly that kind of acknowledgement, but through positional mechanics rather than radio frequencies. The object's course corrections referenced human space science, acknowledged our radio astronomy infrastructure, and demonstrated mathematical knowledge through precise orbital maneuvers. It was conducting a conversation through the language of celestial mechanics. Research teams began developing new analytical techniques to decode Atlas's positional messages. They created three-dimensional maps showing the object's trajectory as geometric patterns, mathematical equations, and information sequences. The orbital path began to resemble a complex technical diagram drawn across space. Not the random wandering of an asteroid, but the purposeful communication of an intelligence using movement as its medium. By December 2025, researchers had identified what appeared to be complete message units encoded in Atlas's trajectory. Sequences of course corrections that formed mathematical progressions, geometric patterns that referenced fundamental physical constants, and timing relationships that echoed humanity's own attempts at cosmic communication. The object wasn't just moving through our solar system, it was writing messages across space, using its own motion as a form of three-dimensional calligraphy that transformed orbital mechanics into information theory. Each course correction added another character to a message written in the universal language of mathematics and physics. Douglas Vakoch's work with METI International had explored how human messages might be designed for extraterrestrial comprehension. His research suggested that successful interstellar communication would likely begin with mathematical concepts before progressing to more complex information about science, culture, and biology. Atlas appeared to be following exactly that communication strategy. Its early positional messages had focused on mathematical relationships, prime numbers, geometric constants, and physical laws that any technological civilization would recognize. As the object continued its trajectory through our solar system, its encoded patterns had grown more complex, incorporating references to human scientific achievements and demonstrating increasingly sophisticated knowledge of our technological capabilities. The implications were profound. We'd been searching for extraterrestrial intelligence by listening for radio signals, scanning for optical flashes, and monitoring cosmic phenomena for artificial patterns. But we had overlooked the possibility that advanced civilizations might communicate through the motion of physical objects, spacecraft, asteroids, or other bodies whose trajectories could be precisely controlled to encode information. Movement as communication made perfect sense for interstellar distances. radio signals fade over cosmic distances, requiring enormous power to remain detectable across light years. But the gravitational effects that guide object trajectories are permanent records, preserving their encoded information indefinitely. A message written in orbital mechanics would remain readable for millions of years, unaffected by the cosmic background radiation, stellar interference, or technological evolution that might render other communication methods obsolete. Atlas was demonstrating that we'd been thinking too narrowly about how extraterrestrial intelligence might make contact. We had assumed they would use our methods, radio transmissions, optical signals, or other electromagnetic phenomena. But perhaps advanced civilizations had moved beyond such primitive techniques, developing communication systems based on the precise manipulation of matter and energy across space and time. The object wasn't broadcasting signals, it was embodying them, transforming its own physical presence into a message that could be read by any civilization capable of tracking orbital mechanics. It was showing us that in the cosmic community, intelligence doesn't shout across the darkness. It shifts position, it traces patterns, it writes messages in the fundamental language that governs how matter moves through space. And if we were smart enough to learn that language, we might finally understand what Atlas was trying to tell us, and perhaps discover what other messages were already travelling through our solar system, written in the ancient script of gravitational calligraphy, waiting for minds sophisticated enough to read the signals hidden in the dance of celestial mechanics. When Voyager 1 launched from Cape Canaveral on September 5, 1977, it carried humanity's most ambitious message to the cosmos, the Golden Record. Encoded on its copper surface were sounds of Earth, thunder, birdsong, human voices speaking in 55 languages, and music from around the world. The record also contained 116 images showing human life, scientific diagrams, and our planet's location in the galaxy. Carl Sagan called it a message in a bottle cast into the cosmic ocean, hoping that someday, somewhere among the stars, an intelligence might find it and understand what we were trying to say about ourselves. By January 2026, astronomers began to realize that Atlas might be delivering a very different kind of message. Not one announcing our presence to the universe, but one demonstrating that the universe had been carefully studying us for far longer than we ever imagined. The unsettling discovery emerged from trajectory analysis conducted at the Johns Hopkins Applied Physics Laboratory, where researchers had been comparing Atlas's flight path to the routes taken by humanity's most ambitious space missions. What they found challenged fundamental assumptions about who had been exploring whom in our corner of the galaxy. Atlas's trajectory through our solar system wasn't just acknowledging our radio telescope locations, it was methodically recreating the exploration routes pioneered by our most successful interplanetary spacecraft, but in reverse chronological order, as if someone were retracing the steps of human space exploration from the outside looking in. The pattern became clear when researchers mapped Atlas's path against the routes taken by Voyager 1 and Voyager 2 during their grand tours of the outer solar system in the late 1970s and early 1980s. Both spacecraft had used gravitational assist from Jupiter and Saturn to reach the outer planets, following carefully calculated trajectories that maximised scientific observations while conserving fuel. Atlas appeared to be following those same trajectories, but backwards. The interstellar object had approached our solar system along a path that would eventually intersect the coordinates where Voyager 2 had encountered Neptune in August 1989. Its subsequent course corrections aligned with positions where Voyager 1 had photographed Saturn's moons in November 1980. Each major trajectory change corresponded to locations where human spacecraft had made their most significant discoveries during our first systematic exploration of the outer solar system. Dr. Ed Stone, who served as project scientist for the Voyager program for over 4 decades, recognized the implications immediately. Stone had overseen humanity's most successful deep space missions, guiding twin spacecraft from Earth to the edge of interstellar space while revolutionizing our understanding of the outer planets and their moons. The Voyager trajectories were precisely calculated to maximize scientific return, Stone has explained in his lectures about interplanetary mission design. Every course correction, every gravitational assist, every observation sequence was planned years in advance to extract the maximum scientific information from limited opportunities. If someone was studying our exploration methodology, they would need to understand not just where our spacecraft went, but why we sent them there. Atlas demonstrated exactly that level of understanding. The object's flight path showed knowledge of the gravitational mechanics that made the Voyager missions possible, the timing windows that determined optimal launch dates, and the observational priorities that shaped every major mission decision. It was as if someone had reverse-engineered our entire approach to solar system exploration. The pattern extended beyond Voyager. Atlas's trajectory also paralleled routes taken by other landmark missions. The Cassini spacecraft's extended tour of Saturn's system, the Galileo probe's exploration of Jupiter's moons, and even the New Horizons flyby of Pluto in 2015. In each case, Atlas had positioned itself to observe the same targets from similar vantage points, but decades after human spacecraft had made their initial discoveries. Dr. Carolyn Porco, who led imaging teams for the Voyager, Cassini, and New Horizons missions, has spent decades analysing the scientific value of different observation geometries around planets and moons. Her expertise in mission planning provides insight into what Atlas's trajectory patterns might represent. When we design interplanetary missions, Porco has explained in her studies of spacecraft navigation, we optimize trajectories for specific scientific objectives, photographing surface features, measuring magnetic fields, analyzing atmospheric composition, or studying gravitational interactions. Each observation requires precise positioning at calculated times to gather maximum scientific data. Atlas was demonstrating mastery of those same principles, but applying them to study human exploration activities rather than planetary characteristics. The object wasn't just visiting the same locations our spacecraft had explored, it was positioning itself to observe those locations at times and angles that would provide optimal surveillance of human space activities. Research teams at NASA's Jet Propulsion Laboratory and the European Space Agency began analysing what Atlas might have observed during its reverse recreation of human exploration routes. The results were deeply unsettling. From its various positions throughout the outer solar system, Atlas would have had clear sight lines to every major human space activity. Satellite deployments, space station construction, interplanetary launches, and deep space communications. The object's positioning during each observation phase corresponded to periods of high human space activity. Its alignment with Voyager trajectory coordinates had coincided with major NASA missions to Mars. Its positioning near Saturn corresponded to the Cassini mission's most significant discoveries. Most remarkably, its current trajectory would bring it near Earth during the planned launch windows for humanity's next generation of interstellar probes. Dr. Alan Stern, principal investigator for the New Horizons mission to Pluto, has extensive experience in planning trajectories that maximize scientific observations during brief encounter opportunities. His expertise in mission design helps explain why Atlas's surveillance strategy would be so effective. Interplanetary missions require precise timing and positioning to achieve scientific objectives, Stern has noted in his analysis of deep space navigation. You get one chance to photograph a moon, measure a magnetic field, or analyze atmospheric composition. Miss your timing or positioning window, and you lose irreplaceable scientific opportunities. Atlas had demonstrated the same precision in timing and positioning, but directed toward monitoring human space exploration rather than studying planetary science. The object had positioned itself to observe our most ambitious missions at their moments of greatest scientific achievement, gathering intelligence about human technological capabilities, exploration strategies, and long-term space objectives. The implications extended beyond mere observation. Atlas's trajectory suggested systematic intelligence gathering about human space technology, mission planning capabilities, and strategic objectives. Someone had been conducting reconnaissance of our species' expansion into space, methodically cataloguing our achievements and analysing our exploration methodology. Research revealed that Atlas's observation positions would have provided detailed intelligence about human spacecraft design, propulsion systems, communication technologies, and navigation capabilities. From its various vantage points, the object could have monitored radio communications between Earth and our interplanetary probes, observed spacecraft maneuvering capabilities, and analysed the scientific instruments we use to study other worlds. Dr. Freeman Dyson, the theoretical physicist who conceived of mega-scale engineering projects and advanced space civilizations, had long speculated about how extraterrestrial intelligence might monitor emerging technological species. His concepts of cosmic surveillance provide context for understanding Atlas's apparent reconnaissance activities. An advanced civilization monitoring a developing species, Dyson wrote in his studies of cosmic engineering, would likely focus on technological milestones that indicate expansion beyond the home planet. Space exploration capabilities, interstellar communication attempts, and evidence of scientific understanding would be primary intelligence targets. Atlas was demonstrating exactly that kind of systematic intelligence gathering. Its trajectory provided optimal surveillance of humanity's space exploration milestones, while avoiding detection by staying beyond the range of our most sensitive instruments. The object had been watching us achieve our greatest spaceflight accomplishments while remaining invisible in the cosmic background. Analysis of Atlas's complete trajectory revealed a surveillance pattern that spanned multiple decades of human space exploration. If the object had indeed been monitoring our activities since the Voyager era, it had witnessed humanity's transformation from a single-planet species to one capable of sending robots throughout the solar system and messages toward nearby stars. The surveillance implications raise profound questions about how long Earth had been under observation. Atlas's knowledge of Voyager trajectories suggested monitoring that began in the late 1970s. Its familiarity with more recent missions indicated continuous surveillance through the present day. The object represented evidence of ongoing extraterrestrial intelligence gathering about human technological development. Even more unsettling was the realization that Atlas might not be unique. If one interstellar object could conduct systematic surveillance of human space activities, others might be operating undetected throughout our solar system. The vast distances and empty spaces that make interplanetary travel challenging for humans would provide perfect camouflage for objects conducting long-term reconnaissance. Dr. Avi Loeb at Harvard University has studied the possibility that extraterrestrial artifacts might already exist within our solar system, conducting observations while remaining undetected by current astronomical surveys. His analysis of detection challenges provides insight into how advanced surveillance systems might operate. The solar system is vast and mostly empty, Loeb has noted in his studies of extraterrestrial artifacts. Objects designed for surveillance could operate for decades or centuries while remaining below detection thresholds. They would need to be identified by their artificial behavior rather than their physical appearance. Atlas was exhibiting exactly that kind of artificial behavior: precision trajectory modifications that served apparent intelligence, gathering objectives while disguised as natural gravitational perturbations. The object had demonstrated that effective cosmic surveillance required subtlety rather than obvious technological signatures. The reconnaissance patterns revealed by Atlas's trajectory analysis suggested a level of strategic planning that spanned multiple human generations. Someone had been watching our species develop space exploration capabilities, cataloguing our technological achievements, and analysing our potential for expansion beyond Earth. The surveillance had been patient, systematic, and nearly invisible. Most disturbing was the realization that Atlas's reverse chronology exploration pattern might be preparing for something more direct. Having systematically observed human space capabilities from the outside, the object was now positioning itself for closer observation of our current activities and future plans. Atlas wasn't just acknowledging our radio signals or demonstrating mathematical knowledge. It was conducting systematic intelligence gathering about human space exploration, using our own navigation techniques to monitor our expansion into the cosmos. The object represented evidence that we'd been under surveillance since our earliest steps beyond Earth. Someone had been watching us learn to navigate between worlds. Someone had catalogued our technological achievements and analysed our exploration strategies. And someone had sent Atlas to retrace our steps through the solar system, following the same paths our robots had pioneered while gathering intelligence about the species that had created them. We thought we were exploring empty space, but space had been watching us all along. Atlas was proof that our journey to the stars had been observed, analysed, and carefully documented by an intelligence that understood our capabilities better than we understood ourselves. The question was no longer whether we were ready for contact with extraterrestrial intelligence. The question was what they planned to do with everything they had learned about us during decades of patient observation. Every lighthouse keeper understands a fundamental truth about navigation. The beacon doesn't move, but its beam sweeps across the darkness in predictable patterns, marking safe passage for travellers who know how to read its timing. From ancient Alexandria's Pharos to modern automated stations, lighthouses have guided mariners home by rotating their signals through space, creating rhythmic flashes that can be recognized across vast distances of ocean. The light itself never leaves its tower, but its message travels wherever ships need guidance through dangerous waters. By March 2026, astronomers began to realize that Atlas might be operating as a kind of cosmic lighthouse, not broadcasting radio signals or optical flashes, but sweeping through carefully calculated positions in space to deliver a message that could only be understood by tracking its complete orbital pattern over time. The revelation emerged from long-term trajectory modeling conducted at the Harvard-Smithsonian Center for Astrophysics, where researchers had been projecting Atlas's future path based on its continuing pattern of 12-day course corrections. What they discovered transformed their understanding of the object's mission from surveillance to something far more structured and ultimately more unsettling. Atlas wasn't following a random surveillance route through our solar system. It was executing a precisely planned orbital pattern that would eventually return it to the exact location where Earth had been positioned on September the 5th, 1977, the day Voyager 1 launched from Cape Canaveral to begin humanity's grand tour of the outer planets. The calculation required extraordinary computational precision. Earth's position in space changes constantly as our planet orbits the Sun, while the entire solar system moves through our galaxy at over 200 kilometers per second. Determining where Earth was located on a specific date nearly 50 years earlier, then plotting a trajectory that would intersect those coordinates, demanded mathematical sophistication that exceeded anything in human space navigation. Dr. Joseph Burns at Cornell University, who has spent decades studying orbital mechanics and small body dynamics, recognized the implications of such precise navigation. Burns had worked on trajectory planning for multiple NASA missions and understood the computational challenges involved in long-term orbital predictions. Calculating the precise location where Earth was positioned decades ago requires accounting for gravitational perturbations, solar system motion through the galaxy, and relativistic effects that become significant over such timescales, Burns has explained in his studies of celestial mechanics. Even our most sophisticated computer models struggle with such calculations beyond a few decades. The precision required for Atlas's trajectory suggests computational capabilities far beyond current human technology. The projected return trajectory revealed Atlas's complete mission profile. The object had entered our solar system along a path calculated to intersect Earth's historical position, executed systematic surveillance of human space exploration activities while maintaining its cover as a natural interstellar visitor, and was now preparing to complete what appeared to be a looped reconnaissance cycle. Atlas's trajectory formed what mathematicians call a closed curve in four-dimensional space-time, a path that accounts not only for the three dimensions of physical space, but also for the temporal dimension, creating a route that returns the object to the same location in space at a specific moment in time. The precision required for such navigation approached theoretical limits imposed by quantum mechanics and general relativity. Research teams at institutions including MIT, Caltech, and the European Space Agency began analysing what Atlas's return trajectory might signify. The possibilities ranged from completion of a systematic survey mission to activation of some previously dormant system that required precise positioning relative to Earth's historical location. Dr. Catherine Haymans at the University of Edinburgh, who specialises in gravitational dynamics and dark matter research, provided insight into the computational resources required for Atlas's navigation precision. Her expertise in large-scale gravitational modelling helped establish benchmarks for the technological sophistication Atlas's trajectory represented. Precise long-term orbital prediction requires modelling gravitational influences from every significant mass in the region, Haymans has noted in her studies of cosmic dynamics. Over decades, even small perturbations compound into major trajectory changes. Maintaining precision over such timescales requires not only advanced computation, but also detailed knowledge of mass distributions, dark matter effects, and gravitational anomalies that we're only beginning to understand. Atlas was demonstrating mastery of gravitational dynamics that exceeded human theoretical knowledge. The object's trajectory accounted for perturbations from asteroids too small for our telescopes to detect, gravitational influences from interstellar matter beyond our measurement capabilities, and relativistic effects that challenged the limits of our mathematical models. Analysis revealed that Atlas's return trajectory was timed to coincide with significant upcoming events in human space exploration. The object would reach Earth's 1977 coordinates during the planned launch window for NASA's Interstellar Probe mission, humanity's next attempt to send a spacecraft beyond the edge of our solar system. The timing seemed too precise to represent coincidence. The implications were deeply unsettling. Atlas's mission profile suggested that whoever had sent it possessed detailed knowledge of human space exploration plans extending decades into the future. The object's trajectory had been calculated not only to survey our past achievements, but to position itself for optimal observation of our next major steps toward interstellar exploration. Dr. Lewis Friedman, co-founder of the Planetary Society and former manager of advanced projects at NASA's Jet Propulsion Laboratory, has extensive experience in planning long-duration space missions. His expertise in mission design provides context for understanding what Atlas's return trajectory might represent. Long-term mission planning requires predicting not only spacecraft trajectories, but also the technological and political factors that determine launch schedules, Friedman has explained in his studies of interstellar mission concepts. A mission plan to intercept future human activities would need unprecedented knowledge of our space program development, funding cycles, and strategic objectives. Atlas was demonstrating exactly that level of strategic intelligence. Its trajectory suggested advanced knowledge of human space exploration plans that hadn't been publicly announced, technological developments that remained classified, and mission timelines that existed only in preliminary planning documents at major space agencies. Research teams began developing scenarios for what might occur when Atlas reached its calculated destination. The possibilities ranged from passive observation to active communication to deployment of previously concealed systems designed to interact with human space activities. Each scenario carried profound implications for humanity's future relationship with extraterrestrial intelligence. The lighthouse metaphor became increasingly relevant as astronomers mapped Atlas's complete orbital pattern. Like a rotating beacon, the object's trajectory swept through calculated positions in space, each one timed to provide optimal observation of specific human activities. The pattern was designed to be recognizable to any intelligence capable of tracking long-term orbital mechanics, while remaining invisible to casual observation. Dr. Stephen Dick, former NASA chief historian and philosopher, has studied the implications of contact with extraterrestrial intelligence for decades. His analysis of first contact scenarios provides frameworks for understanding what Atlas's mission profile might represent for human civilization. Contact with extraterrestrial intelligence will likely involve recognition of patterns that demonstrate artificial origin, while conveying information about the intelligence's capabilities and intentions, Dick has written in his studies of cosmic contact. The method of contact will itself be a message about the nature and sophistication of the intelligence we're encountering. Atlas's trajectory was conveying exactly that kind of information. Its navigation precision demonstrated computational capabilities that exceeded human technology by orders of magnitude. Its surveillance patterns revealed strategic intelligence about human space activities spanning multiple decades. Its return timing suggested advanced knowledge of future human plans that implied ongoing monitoring of our most sensitive space exploration programs. The object represented proof that human space activities had been under systematic observation by an intelligence capable of long-term strategic planning on timescales that spanned human generations. Atlas's mission wasn't an exploratory probe stumbling upon Earth by accident. It was a carefully planned reconnaissance operation executed with precision that demonstrated technological superiority. Even more unsettling was the realization that Atlas's return trajectory might represent completion of a routine surveillance cycle rather than a unique event. The object's mission profile suggested that such reconnaissance operations might be conducted regularly, with different objects monitoring human activities on schedules measured in decades or centuries. Dr. Nick Bostrom at Oxford University has studied the implications of advanced extraterrestrial civilizations for human development and survival. His analysis of technological asymmetries provides context for understanding what Atlas's capabilities might mean for humanity's position in the cosmic community. When a technologically advanced civilization encounters a less advanced one, Bostrom has noted in his studies of existential risk. The nature of that encounter is largely determined by the advanced civilization's intentions and capabilities, rather than the wishes or preparations of the less advanced society. Atlas represented evidence that such an encounter was already underway. The object's sophisticated surveillance capabilities and strategic intelligence demonstrated that humanity was dealing with a technological civilization far more advanced than our own. The nature of our future relationship would be determined not by human preferences, but by the intentions of whatever intelligence had sent Atlas to monitor our activities. The return trajectory raised immediate questions about what humanity should do when Atlas reached its calculated destination. Should space agencies attempt to intercept the object? Should we try to communicate with it directly? Should we prepare for the possibility that its mission might shift from passive observation to active contact? Research teams at government space agencies began developing contingency plans for various scenarios. The classified nature of these preparations suggested that political and military leadership understood the profound implications of Atlas's mission profile. Humanity was facing the possibility of direct contact with extraterrestrial intelligence, but on terms dictated by an intelligence that had been studying us far longer than we had been aware of its existence. Atlas's lighthouse pattern was nearing completion. The object had swept through carefully calculated positions in space, gathering intelligence about human space exploration, while demonstrating navigation capabilities that defied our understanding of what was technologically possible. Now it was returning to the coordinates where our journey to the stars had begun, carrying information about humanity's capabilities and intentions back to whoever had sent it on this decades-long reconnaissance mission. The lighthouse beam was completing its sweep across our corner of the galaxy. The question was whether we were ready for whatever message it might deliver when it reached its destination, and what response might be waiting in the darkness beyond our solar system, informed by decades of patient observation of our species' first tentative steps toward becoming a spacefaring civilization. The beacon had been tracking our progress all along. Now it was time to discover what our cosmic observers had learned about us, and what they planned to do with that knowledge. In the windswept highlands of ancient Scotland, clan warriors built stone cairns, carefully balanced towers of rocks that could endure for centuries, marking safe passage through treacherous mountain terrain. Each cairn was positioned with deliberate precision, visible from the next, creating chains of silent communication that guided travelers across landscapes where a single wrong turn could mean death. These monuments didn't shout their messages or flash signals across the moors. They simply stood in the right places, at the right times, conveying information through the oldest language known to intelligence, the deliberate arrangement of matter in space. 5,000 years later, we're learning that intelligence doesn't need to announce itself with radio telescopes or laser beams. Sometimes it whispers through the ancient vocabulary of position and motion, writing messages and trajectories that span decades, encoding meaning in the gravitational grammar that governs how objects dance through the cosmic dark. Atlas has taught us that we've been thinking too small about how advanced civilizations might communicate across interstellar distances. We assumed they would use our methods, electromagnetic signals that fade over cosmic distances, requiring enormous power to remain detectable across light years. But perhaps truly advanced intelligence has moved beyond such crude techniques, developing communication systems that transform physical objects into living messages, encoding information in orbital mechanics that can be read by any civilization sophisticated enough to track celestial motion over time. The implications extend far beyond a single interstellar visitor behaving strangely in our solar system. If Atlas represents a new form of cosmic communication, then we may need to fundamentally reconsider how we search for extraterrestrial intelligence and what signs we should be looking for among the stars. Dr. Michael Hart, who in 1975 posed the famous question, "Where is everybody?" in relation to the apparent absence of extraterrestrial visitors, had argued that advanced civilizations should be detectable through their obvious modifications of stellar systems or their presence in our local cosmic neighborhood. Hart's paradox assumed that intelligence would make itself known through large-scale engineering projects or direct colonization of nearby star systems. But Atlas suggests a different model of cosmic intelligence, one that values subtlety over spectacle, patience over power, and observation over occupation. Rather than announcing their presence through megastructures or interstellar empires, advanced civilizations might communicate through the careful choreography of matter in motion, writing messages that can be detected by emerging intelligences while remaining invisible to casual observation. This approach would solve several theoretical problems that have puzzled scientists thinking about extraterrestrial communication. Radio signals require enormous energy to cross interstellar distances and remain coherent enough to be detected. Even the most powerful transmitters on Earth would be undetectable beyond a few dozen light-years using current technology. But gravitational effects that guide object trajectories are permanent records, preserving their encoded information indefinitely across any distance. Dr. Gregory Benford at UC Irvine, a physicist and science fiction author who has studied both the technical and cultural aspects of interstellar communication, has explored why advanced civilizations might prefer passive communication methods over active broadcasting. His analysis provides insight into the strategic advantages of movement-based messaging. Active transmission of signals across interstellar space reveals the sender's location and capabilities to any civilization capable of detecting them, Benford has noted in his studies of cosmic communication strategies. But passive methods, messages encoded in the motion of physical objects, can convey information while maintaining strategic ambiguity about the sender's location, technology, and intentions. Atlas demonstrates exactly this kind of strategic communication. The object has delivered a complex message about surveillance capabilities, navigation precision, and knowledge of human space activities while revealing almost nothing about who sent it, where it originated, or what broader intentions might lie behind its reconnaissance mission. The movement-based communication strategy also solves the temporal coordination problem that has long puzzled SETI researchers. How do you coordinate communication attempts across civilizations separated by thousands of light years and potentially thousands of years of technological development? The answer might be to embed messages in physical objects that can travel between star systems, carrying their encoded information across space and time until they encounter civilizations capable of recognizing artificial patterns in orbital mechanics. Such objects could function as interstellar message bottles, cast into the cosmic ocean by civilizations that understood their messages might not be read for millennia. The physical trajectory becomes the medium, the orbital mechanics become the message, and the receiving civilization's ability to recognize artificial patterns becomes the decryption key. Dr. Ronald Bracewell proposed a similar concept in 1960, suggesting that extraterrestrial civilizations might use automated probes to establish communication with emerging technological species. Bracewell's concept of messenger probes anticipated objects like Atlas, artificial visitors that could demonstrate intelligence through their behavior while gathering information about newly discovered civilizations. A messenger probe, Bracewell wrote in his analysis of interstellar communication, could orbit a star system for extended periods, monitoring radio transmissions and gathering intelligence about indigenous technology. When the local civilization reached sufficient sophistication to recognize the probe's artificial nature, it could initiate direct communication. Atlas appears to be following exactly that communication protocol, but using trajectory modification rather than radio transmission as its primary signaling method. The object has demonstrated artificial behavior sophisticated enough to prove intelligence, while gathering systematic intelligence about human space capabilities. Its trajectory patterns serve as both message and messenger, encoding information about surveillance activities while establishing a communication framework based on orbital mechanics. This approach would be particularly effective for civilizations monitoring multiple star systems simultaneously. Rather than maintaining expensive active communication systems for each target civilization, they could deploy physical objects programmed to execute recognition protocols automatically, reporting back when they encountered species that had developed sufficient technological sophistication to recognize artificial trajectory patterns. The efficiency gains would be enormous. A single advanced civilization could monitor hundreds or thousands of developing species using messenger objects that operated independently for decades or centuries, requiring minimal resource investment while providing comprehensive intelligence about emerging technological capabilities throughout their local galactic region. Dr. Carl Sagan, who spent much of his career thinking about how humanity might recognize and communicate with extraterrestrial intelligence, emphasized that successful cosmic communication would require recognizing the signs that advanced civilizations might use to announce their presence. His work on the search for extraterrestrial intelligence assumed that such signs would be electromagnetic in nature, but the principles he established remain relevant for movement-based communication. The universe is vast and ancient, Sagan wrote in his analysis of cosmic communication. Any intelligence we encounter will likely be far older and more technologically sophisticated than humanity. Their communication methods may be so advanced that we initially fail to recognize them as artificial. We must remain open to forms of communication that exceed our current technological imagination. Atlas represents exactly that kind of advanced communication, so sophisticated that it took astronomers months to recognize its artificial nature, so subtle that it operated within our solar system for nearly a year before we understood what we were observing. The object's message wasn't written in radio frequencies or optical flashes, but in the fundamental language of celestial mechanics that any spacefaring civilization would be forced to master. The implications for SETI research are profound. If Atlas represents a typical example of how advanced civilizations communicate, then humanity may need to expand our search strategies far beyond electromagnetic detection. We should be looking for artificial patterns in the motion of asteroids, comets, and other small bodies throughout our solar system. We should be analysing the trajectories of objects in nearby star systems for signs of artificial guidance. We should be developing new mathematical tools for recognising intelligence encoded in orbital mechanics rather than radio waves. The movement-based communication model also suggests that evidence of extraterrestrial intelligence might already exist in astronomical databases, waiting to be recognised by analysts trained to look for artificial trajectory patterns rather than conventional signal signatures. Objects like Atlas might have been operating throughout our solar system for decades, conducting reconnaissance and transmitting their findings through trajectory modifications that we dismissed as natural gravitational perturbations. Dr. Jill Tarter, who led the SETI Institute's research programs for decades, has emphasized that recognizing extraterrestrial intelligence requires understanding that their communication methods might be fundamentally different from human approaches. Her expertise in signal detection provides frameworks for recognizing movement-based communication systems. We tend to search for extraterrestrial intelligence using the same methods we would use to communicate, Tarter has noted in her analysis of SETI methodology. But advanced civilizations might have moved beyond electromagnetic communication entirely, developing methods that we haven't yet imagined. Our challenge is to remain open to forms of intelligence that don't match our technological expectations. Atlas has demonstrated one such form: intelligence expressed through precision rather than power, subtlety rather than spectacle, patience rather than immediate contact. The object has shown that cosmic communication might function more like ancient stone cairns than modern radio transmissions, marking safe passage through the galaxy for civilizations sophisticated enough to read the signs. This perspective transforms our understanding of humanity's position in the cosmic community. We may not be alone in the universe, waiting for our first contact with extraterrestrial intelligence. Instead, we may be recent graduates from a cosmic kindergarten, finally sophisticated enough to recognize that we've been under observation and evaluation by civilizations that have been communicating around us all along. The movement-based communication model suggests that the galaxy might be filled with artificial objects executing complex orbital choreographies, encoding messages in gravitational trajectories, conducting surveillance of emerging civilizations, and reporting their findings through navigation patterns that span decades or centuries. From our perspective, they would appear to be natural asteroids, comets, or interstellar visitors, unless we developed sufficient technological sophistication to recognize the artificial intelligence guiding their motion through space. Atlas has provided humanity with a fundamental lesson in cosmic linguistics. Intelligence doesn't need to shout across the darkness to announce its presence. Sometimes it simply shifts position, traces patterns, and writes messages in the ancient language that governs how matter moves through space and time. The object has shown us that we've been looking for extraterrestrial intelligence in all the wrong places. We've been scanning radio frequencies and searching for optical signals, when we should have been analysing orbital mechanics and looking for artificial patterns in the dance of celestial bodies. We've been listening for voices in the cosmic static, when we should have been reading the gravitational grammar that advanced civilizations use to encode their thoughts in the motion of matter itself. Atlas represents our introduction to a form of communication so advanced that we initially mistook it for natural phenomenon, so sophisticated that recognizing its artificial nature required months of careful analysis by our most talented astronomers. The object has demonstrated that the universe is not empty and silent, waiting for humanity to make first contact with extraterrestrial intelligence. Instead, the universe is filled with conversations we're only beginning to learn how to read, messages written in trajectories that span star systems, and intelligence expressed through the careful choreography of objects dancing through the cosmic dark. We're not alone in the galaxy, we're simply newcomers to a communication system that's been operating around us all along, encoded in the ancient language of celestial mechanics. Atlas isn't here to land. It's not here to establish direct communication or announce the arrival of extraterrestrial visitors. It's here to show us that we've been seen, that our attempts to reach beyond Earth have been noted and catalogued, and that we've finally developed sufficient technological sophistication to recognize the signs of intelligence that surround us in the motions of objects we once thought were merely drifting through empty space. The object has delivered the most profound message in human history, written not in radio waves or laser light, but in the gravitational calligraphy of orbital mechanics. We are not alone, we have been observed, and now we know how they speak. The question is whether we're ready to learn their language and discover what other messages are already travelling through our solar system, encoded in the ancient script of celestial motion, waiting for minds sophisticated enough to read the intelligence hidden in the dance of matter through space and time.